Assalamualaikum and a very good day. Today I'm going to present about my final year project titled Study of Eco Cleaner Production from Fruit Waste Fermentation using Subcritical Water. Up to 50% of fruits and vegetables in Malaysia are thrown away every year. Food waste is a major culprit that may lead to global warming, and if left to be rotten, they will release methane gas, which is 23 times more dangerous than carbon dioxide gas. Fermentation of fruit waste to produce eco-cleaner detergent can be one of the solutions to this issue. This detergent has a multi-purpose and eco-friendly usage for household cleaning, agricultural pest control, and also wastewater treatment. Pineapple fruit is one of the famous tropical fruit in Malaysia. However, only 60 to 70% of the pineapple fruit was used while the rest is discarded. To avoid further environmental issue, pineapple waste is used for eco-cleaner fermentation in this study. Also, this eco-cleaner idea works for various ways. Firstly, it utilizes pineapple waste from being disposed, and secondly, it produces an environmental friendly, cheaper, and a very useful detergent. Fermentation is a metabolic process in which oxygen is absent and only the stage of glycolysis is completed. In glycolysis, a glucose molecule is broken down into two pyruvate molecules, releasing electron carried by NAD+ converted to NADH. It is then produced two molecules of ATP. During aerobic respiration, with oxygen is present, this pyruvate molecule go through Krebs cycle and oxidation to produce more ATP. However, when the oxygen is absent, these two last stages are bypassed. Further fermentation pathway is needed to complete the metabolic process and to recover the electron transporter and NAD+ from the NADH produced in glycolysis. Here are some of the further fermentation pathway. The first one is alcohol fermentation. Going from pyruvate to ethanol is a two advanced process. Firstly, a carboxyl group is removed from pyruvate and released as carbon dioxide, producing a two-carbon molecule called acetaldehyde. And ADH passes its electrons to acetaldehyde, regenerating an AD+ and forming ethanol. During the acetaldehyde production, acetaldehyde also undergoes acetaldehyde dehydrogenase to produce acetic acid. Next, in lactic acid fermentation, an ADH transfers its electron directly to pyruvate, generating lactate as a byproduct. Lactate is also known as lactic acid, only missing one proton. Next is lactic acid further conversion. Based on a research paper done in 2001, it is stated that several bacteria strains is able to further convert lactic acid produced from the lactic acid fermentation pathway to acetic acid and traces of ethanol without requiring an external electron acceptor. In condition, the fermentation must be acidic and below pH 5 to induce the lactic acid degrading process. This is the research objective. Firstly, this paper will investigate the highest production of organic acid produced from the fermentation of eco-cleaner detergent. Secondly, to analyze the relationship of subcritical water hydrolysis as pre-treatment step with the fermentation maturity time and products yield in terms of organic acid and ethanol concentration. Thirdly, to observe any significant catalytic activity induced by yeast addition in the eco-cleaner fermentation process. Next, this is the methodology used to conduct the experiment of this research. Firstly, the pineapple waste was supplied from Reza Amshar Enterprise. Then, the pineapple waste was sliced into dices and stored in a freezer. The batches of eco-cleaner fermentation is prepared, comprised of batch A1, A2, B1, B2, C, and D. The basic substrate is molasses, pineapple waste, and water with ratio of 1:3:10 respectively. Batch A1 and batch B1 use a 2-liter fermenter, while batch A2, B2, C, and D use a 120 ml fermenter due to time constraint. Next, the fermenter was kept airtightly to avoid any oxygen gas from entering. Lastly, the fermenters were let to undergo fermentation process for 90 days anaerobically. This is the summary of batches used for this research. As mentioned before, this research will be using two different types of fermenter, which is 2-liter fermenter and 120 ml fermenter. However, the analytical comparison and discussion can still be verified due to up to 94% of the fermentation reaction was independent of the reactor scale, proving the transferability of the microbe and its function. This is a subcritical water pre-treatment procedure. Firstly, 25 ml stainless steel reactor was filled with sliced pineapple waste, with the solid to water ratio of 4:20. Next, the reactor's inlet and outlet valves were kept tightly closed to avoid any leaking. The salt bath was then set to 200 degrees Celsius and took around 60 to 62 minutes to fully melt and heat up the system. Once the temperature has stabilized, the reactor was inserted into the salt bath for 3 minutes. After the reaction has completed, the mixture was filtered and the hydrolyzed pineapple waste was collected. The collected pineapple waste were weighed and mixed together with the other fermentation substrate and led to be fermented anaerobically. Next, we will discuss about the result of this research. This is the result of product yield of eco-cleaner detergent. Based on this figure, it can be seen that the eco-cleaner detergent produces higher concentration of acetic acid compared to lactic acid. The high concentration of acetic acid produced can be explained by the fact that both alcohol and lactic acid fermentation pathway occurred in this batch of A1. As explained before, in alcohol fermentation pathway, acetaldehyde is produced, then it undergoes acetaldehyde dehydrogenase to produce acetic acid. Meanwhile, in lactic acid fermentation pathway, lactic acid is produced as a result. However, based on the right axis of this figure, the pH value of eco-cleaner fermentation in batch A1 during the entire process was persistent below pH 5. This condition induced lactic acid further conversion to produce acetic acid and ethanol during the fermentation. Additionally, with lactic acid produced from lactic acid fermentation pathway has undergone further conversion, this step has contributed to the greater concentration of acetic acid and low concentration of lactic acid. Next, this is the maturity time of eco-cleaner detergent. The growth trend and the maturity time of eco-cleaner fermentation is observed based on the product and byproduct of eco-cleaner fermentation. The product is ethanol while the byproduct is acetic acid. This study achieved to observe the fermentation process has stopped at 45th day instead of 90th day. Due to insignificant decrease amount between day 45th and day 65th of both ethanol and acetic acid concentration, hence the fermentation process is strongly assumed to be ended on day 45th and the experiment is not being continued further until day 90th. This is the effect of adding yeast towards product yield. Based on figure A, from the first day until the 40th day, batch A1 produced higher acetic acid compared to batch B1. However, acetic acid concentration in batch B1 increased gradually from the first day until the 55th day, reaching the highest acetic acid concentration of 16,000 ppm. Acetic acid is produced during an AD plus regeneration step in alcohol fermentation pathway and during further lactic acid conversion. As shown on the right axis, the pH value of batch B1 is persistently below pH 5. Thus, acetic acid is produced from further lactic acid conversion. During alcohol fermentation, with addition of yeast in batch B1, the NAD plus regeneration step is escalated and the production of acetic acid becomes greater than batch A1. As for ethanol production of batch A1 and batch B1, based on figure B, ethanol production of batch B1 is persistently higher than ethanol production in batch A1. The high production of ethanol occurring in batch B1 can be explained by the having a specific bacteria added, and AD plus regeneration step together with lactic acid further conversion are enhanced further and thus produce greater amount of ethanol. In addition, it is studied that greater content of ethanol in detergent solution give excellent performance and act as a better surfactant agent. Thus, adding yeast into fermentation substrate of eco-cleaner fermentation is proven to produce a better quality of eco-cleaner detergent. Next is the effect of adding yeast towards maturity time that is being observed based on batch B1 of eco-cleaner fermentation. Based on this figure, it is shown that the maturity time of batch B1 ended on the 60th day of fermentation, which is 15 days late if to be compared with batch A1 fermentation of maturity time. Thus, it is revealed that with the addition of yeast into the fermentation substrate does not shorten the maturity time of the process and does not act as a form of catalyst for eco-cleaner fermentation. This is the effect of subcritical water hydrolysis pre-treatment towards product yield, which has been observed based on batch C of eco-cleaner fermentation. As shown in this figure, after several days of fermentation, there is no significant result showing ethanol or acetic acid produced in eco-cleaner fermentation of batch C. With no account of production happening, it is legit to say that the fermentation process does not occur in batch C and thus, eco-cleaner detergent is not produced in batch C. The condition happened due to wild bacteria denaturation during exposure to the extreme temperature of subcritical water pre-treatment step. In continuity, second trial of batch C, which is batch D, is made with an improvement step of adding yeast together with the pre-treated pineapple waste into the fermentation media. Based on this figure, it can be observed that the highest ethanol production of eco-cleaner fermentation occurred in batch B2 followed by batch D and the lowest is in batch A2. Also, even though batch D has undergone subcritical pre-treatment step, but due to bacteria denaturation during the extreme temperature of subcritical pre-treatment step, the fermentation process in batch D depends solely on yeast and thus does not produce the highest ethanol production of eco-cleaner fermentation. However, this pre-treatment step can be used to shorten the time taken to produce ethanol during the fermentation process. As shown in the figure, the ethanol produced in batch D achieved its highest concentration on third day and the fastest production, compared with batch B2 and batch A2. This can be further explained by the fact that subcritical pre-treatment method has broken down the complex structure into simpler sugar, thus help yeast to consume this carbon supply much faster and easier. This is the effect of subcritical water hydrolysis pre-treatment towards product yield. Based on this figure, it can be observed that the acetic acid production increased from the first day until the sixth day for all the three batches. However, from the sixth day onwards, acetic acid production in batch A2 has declined, but the acetic acid production in batch D and batch B2 continue to increase. On the 8th day of process, the acetic acid production in batch B2 has the highest concentration compared with batch D. The pre-treated batch D of eco-cleaner fermentation does not result in producing the highest acetic acid due to total dependency on the yeast added, since the extreme subcritical water condition has denatured all the present wild bacteria during the pre-treatment step. While in batch B2, the addition of yeast together with the already present wild yeast on the pineapple waste as the fermentation substrate result in a greater number of bacteria available to undergo the fermentation process and produce higher acetic acid. This is the result of effect of subcritical water hydrolysis pre-treatment step towards maturity time that is being observed between batch D, batch A2 and batch B2. Referring to these three graphs, it is shown that the maturity time of batch A2 ended on the 6th day of fermentation, while the maturity time of batch B2 and D ended on the same day, that is on the 8th day of fermentation. Batch A2 ended earlier because fermentation in this batch only depends on wild yeast present on the pineapple waste itself, and hence, the process does not take longer time due to less number of bacteria working on the process. Comparing with batch B2, the fermentation substrate used is molasses, pineapple waste, water, and with the addition of yeast. With the addition of yeast, make the fermentation process become greater and thus prolong the maturity time of eco-cleaner fermentation. In consequence, even though batch D has undergone subcritical water pre-treatment step to break down the complex lignocellulose layer in pineapple waste and to increase the reducing sugar in the fermentation substrate, but this pre-treatment step does not shorten the maturity time to produce eco-cleaner fermentation. Next, as a conclusion, in this research, eco-cleaner detergent from pineapple waste fermentation is produced as an alternative way to prevent health and environmental problems. Also, it is achieved to analyze the acetic acid is the highest organic acid produced from eco-cleaner fermentation process. Also, it is revealed that the pre-treated batch of eco-cleaner detergent does not shorten the maturity time. Instead, the pre-treated batch of eco-cleaner detergent ended on the same day as the non-pre-treated batch of eco-cleaner detergent. Also, pre-treated eco-cleaner detergent result in 26% lower ethanol production and 4% lower acetic acid concentration than the non-pre-treated eco-cleaner detergent. Besides, it is proven that by adding yeast into the fermentation substrate enhanced the ethanol production by 27% and acetic acid production by 12%. But the maturity time takes longer, and thus yeast does not act as catalyst and shorten the maturity time of eco-cleaner fermentation. That is all from me. Thank you.